Hi, the title of my talk today is Electromechanical Platform Removable Overlay for Exploring, Tuning, and Evaluating Reinforcement Learning Platform. Outline of my talk. The motivation, I'll talk about the motivation and purpose, and then go through the journey of the platform development, and I'll give a demonstration, and I'll also discuss an overview about the reinforcement learning, share with you my results, and go through a bit of a discussion, and I'll also share what I'll be doing after the as a follow-up to the project. So inspiration, basically this is very much on curiosity. So I was learning reinforcement learning, and I chanced upon the work. I mean, the introduction to reinforcement learning is the ice lake problem, right? And many of this is run on the virtual environment, like open gym. So I was wondering, how about running it on a physical hardware platform, right? Would the agent still perform as well, right? So that gives me the idea of start doing something like that. Another motivation to actually get me to start doing it is the documentary about Dr. Claude Shannon. So it's very good documentary about his life. So who is Dr. Claude Shannon? Dr. Shannon is the discoverer of the channel capacity limit, right? He discovered that any information channel has a capacity limit, has a limit to how much information it can transmit. So previous to that, people thought that is it even possible to measure the information limit of a channel. So a channel is like a medium for carrying signal from point A to point B. It could be a wire, or it could be even wireless. Let's look at this theorem a little bit. On the left hand side is the capacity of the channel, and then the B is the bandwidth. And then you can see that there's some expression within the bracket is S over N. That is the signal to noise ratio. So basically, it states that the capacity of a given channel is the bandwidth multiplied by the log of this 1 over signal to noise ratio. So signal to noise ratio plays a big part in determining how much a channel can carry, right? How much signal a channel can carry. So this is very important, especially in the information and internet age, right? So with this, we can, the scientists and engineers can determine how many cables and how much of fiber optic channels is required to carry so much, how much information. So, and very important, because of the signal to noise, the impact of noise, shielding is required. How do we improve shielding, right, of a signal carrier? This also includes the mobile wireless signal. So, big discovery, landmark discovery. Dr. Shannon is also very curious. He built a lot of stuff as well, not just a theorist. So one of the interesting thing that he did is the electromechanical mouse, auto-solving mouse, the maze called Theseus. So this mechanical mouse can navigate itself out of the maze. So the amazing thing is that this is done using a 1950s technology, right? So rudimentary relays and electromechanical switches, not even a basic PC. So today, maze solving algorithm is fundamental in learning about robotics and also about machine learning, especially the reinforcement learning. So it's very popular among the schools, universities, where students build and program the robots that are able to navigate itself out of the maze in the shortest time. So you check at this page, Wikipedia, it has a lot of description of algorithms being used. I mean, these are not even the reinforcement learning, right? In a basic logical algorithms, right? So, journal of my journey. So I started printing, right, experimenting with printing in September 2019, and started building, testing the platform in April 2020, and did the coding testing in July 2020. And in August 2020, make some enhancement to it, including the Bluetooth connectivity, power supply circuitry. And in March 2021, I started working on the second prototype. So what are the features? Basically, the features of the platform, what can it do, right? So this platform doesn't require a camera to work. And it can basically is a tilting platform, right, with embedded Hall sensors to detect the magnetic ball rolling within the surface, on the surface. So it can tilt 8 directions: north, east, southeast, southwest, west, northwest. Basically, it can. There's no limit to it, but just limit to this 8 tilt direction. And the algorithms can detect, is modified to detect walls automatically, and also self-balancing. It doesn't have to be on a strictly level surface. It can communicate with the computing module wirelessly via Bluetooth. The platform can be changed, or the maze itself, right? The configuration of the maze can be replaced, interchangeable easily. Because of this, the maze can be a separate unit and be within a container, or even immersed in liquid or gas to provide a change of viscosity. So the original maze or the program itself is modified from Eric Delange's code. So he did an amazing job, built a reinforcement learning self-contained code that analyzes the performance of the agent. The agent in this case is the part moving within the maze, right? The ball, right? I'll explain a bit more later. So his program runs on the software only, right? So there's no physical environment to interact with. So this agent is basically this dot here that navigates itself within the environment, and the goal is to reach the exit. So the agent can move in these 4 directions, namely north, east, south, west, right? And the black dots here are the black cubes here are the obstacles or walls, right? So agent can't actually go through this, right? Have to navigate it and move along the white blocks only. So I work upon and modified the algorithm to work on the physical platform, and also expanded the number of cells, because I need to expand. I need to also allocate a cell for the wall as well. So I expanded this to 16 by 16 maze, and the direction the agent can move also increased to 8, right? So we call this the 8th degree of freedom. Because this is a physical platform, we can also I've also allowed the tilt angles. The tilt angles plays a part, right? Because how much the platform tilts determine what is the speed of the ball rolling or the agent moving. So we'll discuss a bit more about this later. So the platform is built using open source software. So in this case, I'm just using Tinkercad. Okay, I mean, it's very easy to start, but as you get into the details, it can be quite you have to be careful, right? So not really the most ideal for complex design, but it works. So this is the physical platform during the build process, right? Did with 3D printing and some small wire wrapping and hot glue, right? So a bit more here. Okay, so this is the completed top part of the platform, right? The servo providing the tilt in the X and Y direction. So let me give you a demo of this platform running. So screen, this is connected to my PC using a serial cable to provide a bit more stability. At the same time, the algorithm is running on my PC, while the mobile phone is also connected to receive the Bluetooth signal, right? You can control the stage as well. But in this case, it's just receiving the inputs, the output from the stage. So it works by notification. It can tell the position of the agent and the tilt angle and motor. It's tilt the stage, tilt stage and other parameters. I'll explain this a little bit more later. So put it on in a ball, a magnetic ball. So the sensor below the maze will detect the position of this magnetic ball itself. So it's being rolled around based on the tilt. So the principle is simple, right? Detect the agent using sensors embedded on the bed of the maze. Okay. So the visualization of the maze in action. So this agent is being driven around, or the stage is tilting, so the agent rolls around, right? So this is visualized here. So depending on the algorithm, right, this agent at the moment is just exploring, right, just moving randomly to locate the exit. It doesn't know exactly where the exit is. It's not being explicitly programmed in. It's not explicitly being told to the agent, so the agent doesn't even know the direction where it's supposed to go. So a bit a bit more here. So as the agent navigates the environment, it discovers that some portion of the maze, right, cannot be driven to. Like for example, if the node of this agent, there's a obstacle when the stage is tilted not towards the north direction, the ball doesn't actually roll up, right? So because of that, it infers that probably there's a obstruction in front. So at first it's not very certain. It will just label this box as gray, right, light gray, and repeated attempts giving the same results will let the agent will increase the confidence of the agent that probably there's a wall, right? So label it darker gray. So when after a certain tries, it knows that okay, it's very confident it is obstacle. It will be labeled black, and therefore it does not try to or attempt to roll towards this block anymore, right? It doesn't try to tilt the stage northwards, so that to save on the one action cycle, right? It doesn't try to move to somewhere that it can't go to. So as we let the algorithm runs a bit more, then most of the blocks now is black, right? Black color. As you can see, it is still not there yet. It's still discovering. This is basically due to the algorithm, right? So the algorithm is just a basic reinforcement learning algorithm, Q table, SASA. So no special enhancement. So after a few more cycles, the obstacles are all confirmed to be black, right? So we more or less confirm that these are real obstacles. So it doesn't try to move towards the obstacle. Okay. So at the end of the training cycle, right, it found, okay, the exit and is able to navigate towards the exit quite confidently. So this is just a replay mode, right? So it doesn't print out the walls or doesn't display the walls, but you can see that quite quickly it can find the exit from anywhere within the maze or the platform. Okay, so this is the result, right? I'll explain a bit more in the next diagram. So this is the run result for the reinforcement learning algorithm. So what we look for is this, right? Win rate first, right? Win rate versus episode. Episode is how many training episodes. So initially, win rate of 1, that means it can find the exit every time, right? So initially, there's a lot of randomness and win rate is very low. Overall is low, but it inches higher and higher. So the randomness is because of maybe the distance from the exit, or certain cells has not been discovered fully yet. But after it learns more and more about the environment, it basically knows exactly where this itself is, the agent, and able to find exit. So by about 700 episodes, it is able to find it almost 100% of the time. So below here is the cumulative reward. So we assign a reward for the agent, right? So starting at 0. So every move it makes will drain some energy, right? So drain a little bit of energy from the agent. So in this case, we call it a negative reward. So it will take and more reward, because this is a cumulative graph, right? So we see that it hasn't really recovered fully, right? It's still declining. But if we continue to let this run beyond 700 episode, this will eventually rise back, because when it reaches the exit, it will get a big reward, and this big reward would result in a overall positive reward cube. So a little bit about the concept of reinforcement learning. So reinforcement learning basically lets the machine learns like human being, right, or natural, even a simple animal, right? So it doesn't tell the it's an interesting branch of machine learning. So basically, what are the main components within this reinforcement learning algorithm? So we have the environment. Environment is the space where, like the world for this agent, where it can go, and where all the spaces within the world, right, for the agent. The agent is the thing itself, right, that interact with the environment, the active agent that can move itself around and take actions. So the actions, as I described, is what the agent can do within the environment. In this case, that would be the direction. It can move north, east, south, west, and also the other directions, right, the north, east, south, west, and all this, the 8 directions it can take. So, and then the environment will also feedback the state and reward. So state is like exactly where the spot within the environment, the location within the environment. So this so-called world for the agent, it can be this part of the world and that part of the world, right? So in our maze situation, it will just be the XY location of the maze, right? So each XY location may or may not have a reward, right? So in our case, the reward is only at the exit point, right? So if the agent managed to get itself to the exit, so you get a big positive reward. Any other location has zero reward, but it has any action the agent takes will drain a little bit of energy. Okay, so just scroll it up a little bit for you to read. So the agent continuously interact with the environment, take an action, and then it will move to a different location or state within the environment, and that will also give it a reward. So feedback to the agent. So the agent tries to get itself to a location with the high reward, right? With the reward, ideally with the highest reward. So the next graph here is the Bellman equation, which give a overview of reinforcement learning. So Bellman equation on the left hand side gives the V, right? V over S, the value of this state. So each state or the location has an associated value. So on the right hand side, you see that there's this max A, then bracket by this R, S, comma A, and plus the gamma, then V over the S prime. So what is this? Okay, so let's look at this first. RSA. So this is the reward for a particular state action pair. So the agent is at a certain location. It can move north, east, south, and west. So each moving north may give a certain reward. Moving south may give a different reward. So is the reward is not just dependent on the state, but also the action, right? So some new location. So this basically indicates the new location, the value of the new location the agent will be at, right? What is the associated reward? So plus, and what is this? So this is the subsequent location after the next location. And this gamma basically indicates the discount factor, right? So future reward do not have the same value as the immediate reward. Like the $1 tomorrow is not as worthy as $1 I hold on my hand today. I can buy food now, right? Otherwise, I need to wait for tomorrow to get the $1. Basically, that's why we have this inflation. So it tries to look for the best combination, the location with the most reward, right? Will be the value of the state. So the next slide will illustrate this better, hopefully, right, with the diagram. So let's say this is a simplified view of the platform. The agent started from here and then got into here. So we just assume that the agent is now in the middle here, the red circle, the brown circle, sorry. So we know that the exit, assuming that exit value is 100 and the discount factor is 10%. Okay, so we can calculate backwards. Exit is 100, calculate backwards. What is the value of the state next to the exit? So this would be 10% off 100 is 90, and then calculate backwards, this would be 81, and the next one will be 73. So agent is at this cell, right? Based on the reward we calculate backwards is 73. How about this part? The agent can also get to the exit toward taking the path up north, right? So we calculate backwards. This is 81, 73, 66, and in fact this, if agent moves north, the value will be lesser than what it is currently, right? How about moving to the northeast? Northeast is the same, right? Because this is 10% off here, right? There's no path leading to the exit. So this would drop to 66 and 59. So which path the agent should be taking? Of course, it can also move back towards the start and it has the same. This is also a lower value location. So using the Bellman equation, the highest value that you can obtain is taking this part, right? Taking this action to move west, right? So t plus 1, the next step, it should move here, right? So you get itself into a location with better, or state, right, with a better value, and you'll just take this logical step. 81, the next one highest is 90, and by doing so it will navigate itself to the exit. But of course, in this algorithm, how do we know, right? The agent don't even know the state of this, all the states for all the location. That's why it needs to explore, right? It needs to learn and explore. So we add some additions to the Bellman equation to make it work in this real life situation. I mean, for this practical situation. So anyway, I haven't explained here. This is just a wall, right? So we can't actually get from here to the exit, right? So hope this gives a better introduction about reinforcement learning. So this is the run using the standard algorithm. The baseline is 8 by 8 times 4 degree of freedom. So we see that the types of algorithm that we can test is the Q table search, SARSAR, Q table with trace eligibility, SARSAR with trace eligibility, and Q neural network, right? So okay, what is the SARSAR and Q learning? So SARSAR algorithm is a different slight modification on the search, how it's assigned value. So a bit detail you can read out on your own, and also from the references listed later. Trace eligibility is like an enhancement addition to the algorithm, right? So it provides another addition to improve the search and value assignment, right? Back from the exit, calculate backwards, trace back what is the value. So with this trace algorithm, it seems to be able to enhance the performance of the basic algorithms. And over here we have neural network. Okay, so I'll explain this a bit more. It seems like the performance seems to be as good or learning as fast. So earlier I was explaining about the cumulative reward, right? So at first it's negative, but very soon it got positive because it started to discover the exit and able to find the exit. So reward accumulates. So we can see for Q search, SARSAR, Q trace, all these 4 algorithm happens. Even the Q neural network, given enough episode, it would also go up, but now we only limit to 300, so it's just breaking even. Below here, this row is about the win rate, right? So win rate, as discussed earlier, how consistent is it able to find the exit? So you can see that after around 200 episodes, it's able to find the exit very consistently for Q search, SARSAR. Interesting thing about this is that with the trace eligibility, is able to kind of like get 100% search ability only at 100 episode, or even slightly below that. For the neural network, is able to, it seems to be inching up, but perhaps we need to extend the number of the training episodes. So it seems like we do not need the neural network for this simple case. This is a different set of diagram, right? This is comparing the number of episodes required to complete the job, right? The top row here. The bottom row is how many seconds it takes for each episode to complete. So we can see that the number of training episodes is about like less than 250, or with the eligibility trace is like even lower than the half of that. But with the neural network, even 1000 may not be enough And the time per episode, very little, within a few seconds, right? Because of the neural network being included here, everything else seems extremely small. So it could be 1,000 or more seconds per episode. May not be so practical. So let's give a little bit detailed look into the neural network performance. This is for another run. It seems like it works, neural network, right? It will also be able to train, right? This episode is better, right? It's able to train about 350 or is getting up there, but not guaranteed. So this is the performance using the 16 by 16 maze with 8 degree of freedom, right? So I just to reiterate, I run with the baseline on the emulator 8 by 8 times 4 degree of freedom. The degree of freedom again is the direction the agent can move towards. So I also run this 16 by 16 times 8 degree of freedom on emulation, and the next one is 16 by 16 times 8 degree of freedom on actual electromechanical platform. So on the this run, we run on the emulated platform. We can see that the Q search is start learning, but obviously because of the expanded cells and option to move more, right? So takes much longer to learn. 1,000 is a limit that is kind of like practical, right? Of course, we can increase this to the number of episodes. So what we want to see that is able to learn, and the same thing with the Q search with trace eligibility and SASA with trace eligibility is able to learn much faster than without trace eligibility. So neural network, I'll explain a bit more later. So for the same diagram here about the number of episodes required and the seconds per episode. So the number of episodes is like 1,000 because the limit I haven't shown you the expanded ones. Probably that is the next time I present. Over here is the seconds per episode. So seconds per episode, how many seconds required? So it seems like longer, much more time now, right? It increased quite exponentially from the previous run using 8 by 8, right? At the time, the platform is not as complicated. So discussion. So results of the run on virtual platform, emulated platform, and the physical platform shows that there are notable differences. Number one, time taken for each action step. The time taken on the virtual platform depends on the processing power, right, of the computer, and also the graphics rendering power. So we can turn off the graphics rendering. With that, the episode will take faster each step. On the emulated platform, because we are trying to emulate the physical hardware, right? So there's a limit, right? And the physical hardware, of course, right? There's a limit to how fast the ball can roll, right? And also how fast the sensor can detect the ball or the agent. So in this case, it's about 1 second per action. So the second item is the size of the maze. As discussed earlier, right, you can see from the results, the size of the maze impact the complexity of the problem by a lot, right? By 8 by 8 maze has 64 cells. When double, 16 by 16 platform has 256 cells. So this is a 4x increase. So this is self-scaled by a power of 2 factor, right? So we haven't even included the increase of the movement, right, the degree of freedom. with that, then it will increase even one more factor, right, of 2. And if we consider the tilt angle also, the tilt angle is like how steep the tilt is, right? So this steepness of tilt will impact the agent speed, right? The movement of agent speed. So number 3, movement of agent. Due to the free rolling characteristics, the agent can travel across multiple cells, right? This complicates the calculation of max Q, because in the virtual original environment, the agent can only move one step to the surrounding cells, right? But now in the physical platform, it can actually roll far away, right? Multiple cells, even possible to roll to the exit. So it may even be able to roll to the exit, right? So I think this is where the interesting things about the deeper, more powerful learning algorithm comes to play, right? The deep learning, given enough iteration, may be able to figure out that, okay, instead of rolling gently, maybe it can even jerk the platform to kick the ball quickly towards the exit. So this should be would like to evaluate and explore in with more evaluation and experimentation. So coming back to the hardware, right? Why we want to use hardware, right? Real world is messy, right? It's not so predictable. In the learning environment, the platform is very simple and you do not need to account for so many factors. It's great for learning, but or to test the robustness of the algorithm on the real world environment, you need to have it on a physical or at least a very detailed model of the environment. But if you do a detailed model environment, you'll increase the complexity very much, right? Even then, it may not reflect the physical environment accurately 100%. And then if you want to make changes, then you have to change the model, right? Whereas the physical platform, if we make the platform to a standard, right, then we can evaluate on a known standard hardware platform or configuration of the maze. So how about camera? You have seen many papers using cameras to do the search, right? Which is very popular. Camera is very powerful, has high resolution, but it also demands a lot of processing power. And it requires a controlled lighting environment. It requires high contrast, right, between the agent and the surrounding structures of the maze, right? So it has to be standing out. Well, because of that, it cannot work with the ball or the agent concealed, right? Let's say it enters into a concealed space, it can't see, it can't work. Or within, let's say, immersed in liquid, and then the refraction changes the light, then it would not be able to work that well. And of course, because of the camera, it needs to look from top down. You will be obstructing, right? So it has to have a certain height looking down. Right? So you have to be high enough, because if you put a 3D structure wall, then it may have shadow, right? So it needs to look much higher up. So that will be a limitation. And when the platform tilt, ideally the camera will also follow the platform tilt angle, right? So if you want to do it fast, then there will be a lot of structure to move around, may require a lot of support. Practical limits. So there are still challenges with this initial platform. Basically is made using 3D printer, right? So it's not very strong mechanically, right? And reliability may not be so ideal. And the sensing accuracy and stability can still be improved, because right, when the sensor may not exactly pick the location of the agent or the ball right, consistently, right? So of course I try to make averaging of multiple measurements to take into account the average, but doing too much of that will also slow down the acquisition of signal. And need to consider power supply stability, especially if this is to be battery operated, because if we move the stage quickly, right, it will drain the power, right? The current drain will be high, and subsequently the voltage will drop, and this may affect the readings. And the operation throughput is very much depends on the physical environment, right? As I mentioned, practical is about 1 second. So conclusion, the electromechanical platform offers the following benefits. Real world is messy, not 100% predictable. Evaluate algorithms on the physical real world platform, especially if this platform is duplicated and according to a standard, right? Then researchers can share, okay, this is the platform, how well this algorithm is working on platform A, the maze A versus maze B and maze C, right? So also allows direct and immediate feedback of algorithm performance following intricate variations in the environment. For example, right, I have this platform, I can put some dust onto it, some sand, and see whether it still works as well. And then maybe immerse inside a liquid, right, and see, okay, how well this algorithm still works. So again, I mentioned about the model, right? So we can create detailed model, but how much work is required, right, to model exactly, right? Explore and train algorithms for search efficiency on one or across multiple mazes. So we can train one algorithm and make some changes, right? Take out some of the walls and put something else and see what happens. Is it still able to work well, right? Robustness of algorithm. So this is a mechanical platform will provide a common reference for researchers and enthusiasts to share and reference work, right? Another thing about this is that it's quite fun to watch the algorithm in action, right? Physical learning taking place. So it will be good for educational purpose and even a showcase. So follow-up, I've actually done a bit of follow-up work on this with more professional 3D modeling. That hopefully and also with the better sensors. So this should improve stability and hopefully throughput as well. So was also considering including some adjustable dials on the physical platform to adjust exploration rate, learning rate, and things like that, right? You'll be able to see exactly instead of changing on the algorithm. So the next step would be mobile app, right? Also maybe a web app to communicate directly. The learning can take place in the cloud, right? To harness the energy of the platform. So interface for the cloud for algorithms to be downloaded and uploaded. So I think this would be helpful if we have a community, then we can share the training, right, from one researcher to the next, right? Just upload and share and discuss how the algorithm works, right? You can verify with different researchers. So this is the PCB for prototype number 2. Okay, so references here, right? Okay, so references. So I'll share a bit about the Python module also that communicates with the hardware. So this is the Python module that's running on my PC. So basically this is the interface part, right? We can connect with using both serial and Bluetooth. So what are the parameters? So we will get the position of the agent, X position, Y position, right, from the platform. the acceleration gyro. So this will be able to detect the stability, right, and also the whether the platform has stabilized or is still in the process of moving. And we do some handshake communication, right, looking for the correct port to connect to. Connection itself, right, where this one is just basic zero communication protocol for connecting and disconnecting, right. This is for Bluetooth notification. So Bluetooth can send the notification of the platform status to a Bluetooth device, right. You can also send the move command back to the stage, right, using Bluetooth. So okay, so some of the inputs that we can get back from the stage, the button status as well. So it just formats the signal pan it accordingly. So over here we have the main program. So this is just a test program to make sure that the platform is able to move and sense back objects accordingly, right. So just drive the platform in all directions, in all angles slowly. So this is for reading the signals back from the stage. So what we can send to the stage is the action and the strength of the action. So action is basically the direction of movement, not east, south, west, okay. And then the strength is what is the tilt, right. So in practical terms, no, we shouldn't have continuous. We could, but that may not give too much of a purpose, complicate the learning process. Okay, so I've also written the paper that is peer reviewed. So it's available. I will upload it. This is not the latest version, but I will upload the latest peer reviewed version. And you may contact me at my LinkedIn for collaboration and discussion. Thank you for your time.